This video is on other norms and distances. So we have defined what a metric space is. We have defined already balls and open sets and started to study some of their properties. But where things get interesting, especially with applications in mind, are introducing different distances and different norms on the same space. They're good for different applications. In visual applications, certain ones are needed in textual data analysis. Other distances may be appropriate. So these different distances exist on the same space, namely Rn. Rn can be thought of as our set of data elements, which are vectors of some sort, with n components, x1 through xn. Now, the distances that are often defined, they satisfy certain assumptions like translation and variance that occur in practice many times, consist of actually first studying norms. And this is a continuation of the norms video. So if you haven't seen that, you might want to look at that. I won't here recall the definition of a norm, but one can define different norms, the so-called P norms, and these make sense as long as P is between 1 and infinity. It can include 1, but for this definition, it does not include infinity. And this is simply defined as you take the sum of the absolute values to the power P, then raise that to the 1 over P's power. So when P equals 2, this is Euclidean distance. And when P equals 1, this is the so-called taxi cab distance that you can Google. And it consists of the distance between 2 points, say in the plane, is the sum of the distances in the x component, the differences in the x component and the y component. One small remark is that there is a definition that makes sense for P equals infinity. I will not discuss that because the proofs for that are quite different. For P equals infinity, the norm is just the maximum of the absolute values. One can show all these properties for that, but those are proven quite differently. Now, in that lecture on norms, we had a bunch of properties that the norms need to satisfy. They need to be positive. That's sort of automatic because we have absolute values. They need to be homogeneous. This is a direct computation. And if they are 0, the only vector that should make them 0 is the 0 vector. And the expression makes that quite believable because if this expression is 0, the only way for that to be the case is if the expression inside, in fact, is 0, but that is only possible if each of the terms is 0, and that's then only possible if each of the components is 0. So this is common for distances and is familiar from many other examples as well. The difficult case is always the triangle inequality. That's the case for distances and norms as well. For norms, what the triangle inequality looks like is similar to the absolute value is that the norm of x plus y is less than or equal to the norm of p, norm of q. And this is called the Minkowski inequality. The way to prove it, it's not an easy thing to prove, but it involves some nice inequalities. So the goal of this lecture mostly is to is to prove that inequality. So for that proof, the main thing is Hölder's inequality, which generalizes Cauchy-Schwarz. It works for a general exponent p, just like in the statement we want. And first we need to define what is called a dual exponent. We say that p is dual to q if we have this equation. 1 over p plus 1 over q is equal to 1. This duality relationship is particularly important in convex optimization, convex geometry, but also comes up a lot in analysis, harmonic analysis, and many other places. It's called a duality because if q is dual to p, then p is dual to q. So this is a symmetric relationship. Every number between 1 and infinity has a unique dual, and it's given by p over p minus 1. You can solve this equation. So this defines the dual exponent. And the q from now on is the dual of p. So if you could add a statement to this Hölder's inequality, if p is between 1 and infinity, and 1 over p plus 1 over q is equal to 1, then the following thing is true. So before we go into Hölder's inequality, there's a simpler case of it, or related statement that we will need. And this is just a statement of real numbers, an inequality for real numbers. If A is a non-negative real number and B is a non-negative real number, so assume, then AB, the product of A and B, is less than or equal to A to the P over P plus B to the Q over Q. And this proof is an exercise in single variable real analysis. It looks like it has two variables, but it can be reduced to a single variable problem. I'll go quickly over the main steps of the proof. We define a function phi ba, that is the left-hand side minus a to the b over p. And what we want to show is that this is less than or equal to b to the q over q. And the proof how it does that is actually it shows that the maximum of the function is b to the q over q. And it goes in a few steps. The first step is that there is a maximum in 0 infinity. The second is that it's differentiable. This is almost obvious. And the third is that, okay, you have an interior maximum, so the derivative must be equal to 0. If you solve that equation, you only have one solution. That is b to the power 1 over b minus 1. And finally, if you evaluate the function at that point, which is the maximum of the function, then you get b to the q over q. So these claims together then will very straightforwardly give that claim. So we really are just maximizing phi b over a. Why we have to be careful is that we cannot just apply extreme value theorem because the domain is unbounded. And open. So it's not even closed. We have to make sure that the maximum doesn't sort of go off to infinity, and we have to make sure that it's not attained at 0. So, well, if we look at phi b of 0, we get 0. Okay, so that's not a possibility. If we look at the limit as a goes to infinity of phi b of a, well, p is bigger than 1, so the second term here will dominate. So here we are using because p is greater than or equal to 1. And these are things that you should know how to verify, but I don't want to now spend time on. So it goes up to negative infinity at infinity. It is 0 at 0. And if I compute the derivative, okay, this is already assuming part 2, then the derivative at 0 is equal to just b. And B was assumed to be, let's assume for this part to be non-negative. So the derivative here is non-negative. Okay. Well, first of all, if B is equal to 0, so we don't want the, I want the derivative actually to be positive, so I want to exclude that case. So if B is equal to 0, then VB of A is just equal to minus A to the B over P. And this is certainly less than or equal to 0, and which is less than or equal, which is just equal to what we want it to be, B to the Q over Q. So we are done in that case. So only case of interest is B strictly bigger than 0, in which case phi prime at 0 is strictly positive. But that means that the maximum of, or the supremum of this function has to be positive, because the derivative at 0, the slope at 0 is positive, so there exists a small, to add detail here, so there exists a small h such that phi b of h is bigger than phi b of 0, which is equal to 0. So there exists a function value where things are positive. Now, because of the limit property, there exists some m such that phi b of x is less than or equal to, say, -1 for all x greater than or equal to m. So if you're going to minus infinity, you'll become less than any bound that you prescribe. So for example, -1. Now, 0m is a closed interval. By extreme value theorem, since phi b is continuous, there exists a maximum in 0m, and phi b of, and let's call this maximum point A star, phi b of A star has to be positive, well, because it's the maximum, so it has to be bigger than this value that we gave before, which was positive. So you know that the maximum, at the maximum you're positive, and therefore A star cannot be equal to 0 or m. Because we know that at phi at 0, phi b at 0 is equal to 0, and we are positive, and phi b at m is less than or equal to -1, so it cannot also be the case that we are. So that part is done. So we get a maximum where the function is strictly positive. Now, I didn't fully, this is also a global maximum, but which is easy to show. So also global maximum, but we won't need it. Well, we do need this. So it's also a global maximum. And why is that? Well, if y is inside 0 to infinity, then either y is inside 0m, in which case phi b of y is less than or equal to phi b of A star, because it's the maximum inside that, or y is bigger than or equal to m, in which case phi b of y is less than or equal to -1, which is certainly less than phi b of A star. Either way, phi b of y will be less than or equal to phi b of A star for all y, and it's a global maximum. Okay, so that was that. Now, there were two things that I erased. 2 was that it's differentiable. This is easy to show. It's a product and sum of continuous functions. 3 was that this derivative is equal to 0. Well, this also is part of extreme value theorem because it's differentiable. This gives you phi b prime a star is equal to 0, and then just solving this equation, called the expression here, it gives you, if you differentiate that in a, then that gives you b minus a to the p minus 1 is equal to 0, or a is equal to b to the 1 over p minus 1. So now if you plug that into the function, what we get is a star b minus a star to the p over p, and this gives you b to the 1 over p minus 1, b minus b to the p minus 1 over p. So, adding these exponents and simplifying, this is p over p minus 1 times 1 minus 1 over p. And then using the duality, 1 over p plus 1 over q is equal to 1. One gets that this is the same thing as b over q over q. So this was the global maximum. So we know, therefore, that ab minus a to the p over p is always less than the global maximum, which is equal to b to the q over q. And then this is what we wanted to show by moving the term on the other side. So with this lemma, we can now prove Hölder's inequality, the step 2 on our way towards Minkowski's inequality, and this is itself very interesting. So for all, it states that if you have real numbers, ai and bi, then the sum of the product of those can be estimated from above by a product of two things that are norms of b and q. And those norms are the p norm and the q norm of that number. One remark is that these could be, by sending n to infinity, taking the limiting argument, one can justify that taking n equals infinity here. But I will prove only the finite case for now. And it is a consequence of the lemma applied to appropriately renormalized sequences of numbers. So what we do is we divide a by its norm. We divide b by its norm. So what we now have is that sum over ai tilde to the power p is actually equals 1. And sum over bi to the q, bi tilde to the q is also equal to 1. Why do you get 1 is that when you raise to the power q, these powers go away. And then you get it, the denominator is equal to the numerator, and therefore equal to 1. Now this is nice with the lemma in mind, because what the lemma tells us is that the product of these two things, term-wise, is less than ai tilde to the power p over p plus bi tilde to the power q over q. Well, by what we just said, the sums of those are 1, so we get 1 over p plus 1 over q is equal to 1. So let's write this out differently. ai tilde over its norm, p norm, and this sum is from 1 through n, Let's use a different index to not confuse with the other index. And bi tilde. So ai tilde is equal to ai, absolute value of ai, divided by that. Bi tilde is absolute value of bi, divided by sum of k equals 1 through n. And we can use still j here, just for clarity. Bj to the power q, 1 over q. So this is now less than or equal to 1. So if you multiply, each of these terms has the same denominator. We can multiply it on the other side, and what we get is exactly what we want. Sum of ai bi is less than or equal to the p norm of ai. And I just changed the index here to match with the statement. And then the same for the b's, but with the q, the dual power q. So we get Hölder's inequality. And this is the one that gives us Cauchy-Schwarz when P equals Q is equal to 2. And then that allows us to read off the answer, and the proof is complete. Now, finally, we can combine this Hölder's inequality to get Minkowski, what we wanted. So norm of x plus y is less than or equal to norm of x plus norm of y. Here, we estimate. Initially, we start from what on the left-hand side, raised to the power p, so sum of xi plus yi to the power p. We split this up into two terms. The first one will be our ai. The second one is not quite. We first use standard triangle inequality to split it up into two terms. Then we split the sum into two parts. And then we think, okay, how do we get something that looks like what we want here on the right-hand side? Now, this involves xi to the power p. So we want to raise here the second term to the power p, and here we want to raise this to the power q, but then that causes this to be raised. Both cases, we want to raise this to the power p, and then the other part to the power q. So if we apply that Hölder blindly, what we get, well, both of them will have a factor, sum over n to the n, xi plus yi p minus 1 times q, 1 over q. And then we will have the desired terms, xi to the power p, 1 over p, plus yi to the power q, p, 1 over p. So now we have to regroup these a little bit. So let's remember what the dual exponent relationship was. Go back a little bit to when we computed it towards the very beginning here. So q is equal to p over p minus 1. This is good for us. So recall, q is equal to p over p minus 1. So this thing here is the same thing as sum I equals 1 through n, xi plus yi to the power p. So we're starting to see what we really want. And then to the power p minus 1 over p. And then what we have here is norm of x to the p plus norm of y. Okay, and let's write the inequality that we got. So norm of x on the left-hand side, we started off from norm of x plus y, p to the power p. And we got that this was less than, and this again involves norm of x plus y to the power p and p minus 1 over p, then times norm of x p and y p. So these p's cancel. We divide out power p. We're left with one extra one here. And what we get is indeed x plus y. The norm p's norm is less than or equal to x norm p plus y p. And this concludes that this triangle inequality is true. So now this is a norm. How do we build a metric out of it? Well, similar to the absolute value, we define the distance between two vectors or 2 points is the p distance general. It's the difference in the p norms, or for any norm, it's just the difference in the norms. So I'll state this for a general norm. Well, this similar to norms, distances have properties. So let's verify them now. Well, distance xy is bigger than or equal to 0 because norm of anything is always bigger than or equal to 0 for all c. In particular, it's true for x minus y. Now, if distance xy is equal to 0, then what we have is norm of x minus y is equal to 0. Well, by the 0 property of the norm, this means that x minus y has to be the 0 vector, but then x has to be equal to y once we add that term to the other side. And this is what we wanted to show. We started from our assumption, we got our conclusion. Symmetry, well, distance x to y is equal to norm of x minus y, which by homogeneity is the same thing as y, norm of y minus x, which is the distance yx by definition. And finally, triangle inequality. Well, if we have 3 points, x, z, y, distance x to z is the same thing as norm of x minus z. And this is the same thing as x minus y plus y minus x. So we add and subtract y. And this is less than or equal to norm of x minus y plus norm of y minus z, which by definition is distance x to y plus distance y to z. And this verifies indeed that distance is less than going by an intermediate point. This verifies the triangle inequality. So all these norms, they give you distances. So our conclusion indeed is that if we define the distance between 2 points to be sum of the differences in the components raised to the power p, taking the 1 over pth norm, and I is here, and p here is between 1 and infinity, then this is a distance function. In the process, we got also Hölder's inequality, Minkowski's inequality, and then there was this useful lemma that we used for them, namely AB is less than A to the power B, or plus B to the power Q over Q. That's all for now. Thanks for listening.